Yeah, so we have exciting lecture for you today, natural policy gradients. The lecture slides are already online if you want to download them. Why this shouldn't work, right? I plugged this guy here, right? Mm-hmm. Oh, sorry. I can do that next time on blank screen. Okay, perfect. We're done. So what is today lecture about? Let's look at actor critic. Okay, this is what we discussed last time. In fact, in two parts of our lecture. And we said here is a particular form of policy iteration for stochastic policies that can handle discrete actions or continuous actions, okay? And because we have stochastic policies, I got a question last time, we do not need epsilon grid exploration. We just sample from the policy. The only thing we want to ensure is that our policy does not collapse, okay? That's why there was a gradient that trying to increase the entropy of our policy. And this is exactly what you're going to implement in homework 2, okay? No epsilon grid here. We just sample from our policy because our policy is stochastic. We couldn't do that in DQN. Why we couldn't do that in DQN? Why there we had this epsilon greedy? Why we had to explore with epsilon grid exploration for deep Q networks?
Deep Q networks, we were making our target policy as a max over the QSA.
Yeah.
And then max would like cause that collapse.
Yeah. So it was a deterministic policy. That's why, right? So we don't want to, for the same state, always sample the same action, right? That's why we added some noise on our policy. Here, our policy is stochastic. As long as we ensure that its entropy doesn't go too little, we can just sample actions from our policy directly. Is this clear? Okay. So today, the whole lecture is about alpha. What you see there in red, what should be our step size? Given some collective experience, how many gradient steps I need to do to update my policy before I recollect training data? Okay? Why this is important? I'm pretty sure in supervised learning, you may potentially need even have to have a lecture to talk about step size, right? Everybody would just say, oh yeah, pick a learning rate, do some, instantiate the 1 to 5 experiments, sample their learning rates, see which one does better, that converges and so on, doesn't blow up, and that's it, stay with that. Well, in our case, things are more complicated because we have this dependence between policy and data collection. In supervised learning, the data do not change. Here, as the policy changes, the data changes because the policy is deployed and you collect new trajectories. So you really don't want to change your policy too much. Also because those advantages, okay, how good a particular action is in a particular state, depend on the particular policy pi. Okay, if you change the policy too much, those advantages are not anymore valid. Okay, is that clear? That's why we iteratively collect trajectories, recompute advantages, update our policy, recompute advantages, and so on. So there isn't an interplay here between how much I can update and move my policy given those advantages, given that I really don't want to change it too much, right? I really don't want to change it too much. So you will see why adjusting this step size alpha is a little bit tricky. Now, what we will be using is the off-policy gradients, the off-policy gradients that we discussed last time. Why this is the case? For the very simple reason. I have a particular theta, I collect trajectories, okay, I compute my advantages and so on. Now I'm about to do gradient descent steps. Am I going to do one gradient descent step? No, I'm going to do multiple ones, right? I'm going to do multiple ones. So during this gradient descent, of course I become off policy. I left already my theta, which was used to collect the trajectories. Do you see what I mean? So naturally, because we did multiple gradient descent steps, we were always off policy, okay? But now I'll show you how very simple things are, like terribly simple. Do you remember in last lecture, we had done the following simplification? We considered an expectation over states and actions sampled from my old policy, parameterized by neural weights theta old, okay? And the objective with respect to the present parameters theta was essentially expectation of the sum of rewards for different actions, where each one is pre-multiplied with the probability of that action under the present theta divided by the probability of that action under theta old. Is that clear? It is clear. Okay, so now here is my question. I want to take the gradient with respect to theta of that quantity. Okay, what do I have to do? Who would like to tell us? The expectations, right? I know how to take care of the expectations. I'm just going to use sample of trajectories, all right? But basically, do you have any problem putting a gradient with respect to theta in front of this expression and pushing it inside the expectation and taking essentially the gradient of p theta of alpha t condition st divided by p theta old and so on? So who thinks that this is a correct expression? And that we can approximate those expectations with sampling? You think it works? Sounds good. How is this different than what we had done in our policy gradient lecture, where we really got worried when we pushed the gradient inside the expectation? How is this expectation different? Yes?
I think it's because it's with respect to sampling from like the whole policy and different data.
I think your colleague is trying to say the following. Same as before, we have an expectation. However, the distribution inside the expectation does not depend on the parameters with respect to which we want to take the derivative. Okay? The expectation in the previous lecture was not with respect to theta old, was with respect to theta. Okay? Here, the expectation with respect to p theta old, which is a constant. Okay? Of course, we can push the derivative inside the expectation, and we're done. And we can approximate the expectation very easily just by sampling trajectories for our p theta old. Okay? And everything works out. And I know how to compute the gradient of p theta alpha. P theta alpha is differentiable, is a neural network, right? That takes as input the state and spits out distribution over actions. And everything works out. Do you see? Now, if you want, you can also do our trick as before and do, divide and multiply with p theta alpha and end up with something like that. The two things are equivalent. Do you see? You do not need to do it in this case, because the distribution in the expectation does not depend on theta, which is the parameter with respect to which you're taking the derivative. Is this clear? Okay, great. So far we understood why these two things are equivalent. We understood why we will always be using the off-policy version of that policy gradient, because we take gradient steps, so naturally we are far away from the initial theta. That's all we're saying. And let's move on and see why the step size is actually important. Let's see why. Okay, so this is our reinforcement learning objective, and we said it has this type of gradient. And you know what? In supervised learning, we have this other objective. This is specifically imitation learning, where A hats are expert actions. And okay, sure, we can put a regularization there for the weights of the neural network, and has these corresponding gradients. And in both cases, we want to take a step, a gradient step. So now the question is, why we do not worry much? On imitation learning lecture, I'm not going to talk to you about the step size. Do you see? You just, guys, I'll discuss other things like distribution shift and so on, but nobody's going to discuss about the step size. You're just going to pick a learning rate and do your gradient descent. While now we have a whole lecture about the step size. I think this is what we're trying to see in this slide. Why there is this big difference between reinforcement learning and imitation learning on the importance of the step size. Let's see why. So the step size is critical for reinforcement learning. If your step is too big, then you may end up to a bad policy, right? Because you actually optimized the policy and the advantages are not valid anymore under your change theta. And you may end up with a bad policy, and then the data you'll collect are going to be no good, and you'll get stuck. You won't be able to recover. While in supervised learning, the only thing that can go wrong if your step size is not good is the training curve not to go down, and then you're like, okay, let me just restart it, and that's it, with a smaller learning rate, okay? So the data stays the same. The supervised data never changes. It's the same state annotated with expert actions. While here, as you change the policy, your data are going to change. Now, the second thing is, if the step is too small, then you are not using your experience efficiently. And if you want to write a paper, the only thing you care about is to say, I use less data than this other competitor baseline. So if you use more data, if you take 10 little steps, you're going to naturally collect more trajectories than your competitors. Okay, so this is very important. That's all we care about, the sample efficiency of our reinforcement learning. And here now, here's the big problem. The big problem is as follows. So, by the way, here's theta and theta nu. We're maybe using theta, theta prime, theta, theta nu, theta all, theta nu to denote all the new policies. Here, this policy is a Gaussian policy over continuous actions, all right? So you have some nu and sigma parameterized of the Gaussian with respect to theta, and here is the new parameters, that's all. And the problem is the following, that looking at the Euclidean distance, or the norm of theta nu minus theta old, the norm of that vector, cannot easily tell you how much the policy changed. Do you see what I mean? So it's, and let me actually have a very nice slide on this. So here is a slide. Imagine I have a very simple policy that has only two actions and only one parameter theta. Only one parameter. And theta takes the following values, 0, or takes value 2, or takes value 4, okay? And here is a policy, which is a sigmoid of that theta, parameterized with that theta scalar parameter. And with probability sigma theta, you choose action 1. The probability 1 minus sigma theta, you choose action 2. And here's the problem. Once you start from theta being 4, then here are how your probabilities over your two actions look like, and they sum to 1, of course. And once theta becomes from 4, 2, which means the delta theta is how much? Right, or minus 2, if yes, depending whether you take the norm or not. Then you have this policy, which actually the probabilities are kind of similar-ish to the first case. But then you take two more delta theta again equals 2, and you see how dramatically the policy changes between the step 2 and step 3. So what does this slide show? It shows that for the same step in your parameter space, delta theta equals 2, the policy, depending on where you are in that parameter space, around which theta, changes more or less dramatically. Yes?
Could we quickly revisit why it's a problem to have the alpha too big? Because we did too off policy and we were doing that approximation where we were assuming that we're still close to the...
Yeah, so when you optimize and you try to maximize some advantages, right? Those advantages, if you remember, are parameterized with policy pi. If the policy changes dramatically, then these advantages are invalid because these advantages can be computed assuming that you will be, is the goodness of a particular action in a state, assuming you use this policy pi onwards. Do you see? Mm-hmm. Yeah. But do you see this problem? And we have a way to, let's say, talk between us about how different parameter vectors are, and we talk about the norm of the change. How do we talk between us about how different policies are? Policies are probability distributions over actions in a particular state. So we'll measure the difference with a KL divergence, okay? So that's how we'll quantify how much a policy changes after a change. But in any case, the conclusion here is the following. The same parameter step, delta theta equals minus 2, changes the more or less dramatically depending on where in the parameter space you are. Let's see how we're going to resolve this. So what is your suggestion, guys? What is your suggestion? We're going to do something extremely intuitive. We're going to start, and this is the notation we'll be using. We're going to start with the following thing. We know that when we take gradient descent, essentially we start from a particular theta and we say do not change that much the delta theta, the norm of delta theta not to be too large. That's what we're saying. Okay, make little steps and so on, and recompute the gradient because the gradient is valid locally. Okay. Now the problem is that this delta theta, this this norm of d, where d is the theta nu minus theta old, cannot tell you how much the policy changes. Okay, that's the problem. And when I take steps, I want to take into account how much the policy changes. So instead of bounding the norm of the parameter change, I'm going to bound the KL of the policies on each state instead. Does this make sense? Yeah. But by the way, why we don't we want to bound the d in the first place? Well, because we took the gradient in a particular location of our parameter states in the first place. Okay, so we call this the natural gradient descent. It's essentially the change on my parameters that I take while taking into account the KL of the resulting policy, right? The policy that results if I change my parameters. So why this is good? Because now it is easier to pick that distance threshold, epsilon. Okay. And just to remind you, this is what KL is. This is how we define it for discrete distributions and for continuous distributions. Okay. And here in this lecture, we have both, because we said we have policies that can handle both discrete actions as well as continuous actions. Okay. Question so far? Yes.
Since KL isn't symmetric, how does changing the order of, like, if you're changing the KL between the old and new policy, the new and old policy affect the nature of the policy gradient?
Well, we take the KL of the new, of the old, to the new.
Yeah, so if you switch that, how does that affect the policy gradient?
I see. Good question. I do not know. I need to check about this. Let me think. Does this make sense to consider the other way around? Well, the truth is that we need to be able to take probabilities of the items. And if we don't have the next theta yet, how we're going to evaluate those, right? Yeah, but let's see. Let's go through the math and see if you can switch around the order. All right. So basically, let's look at this objective now. So it's the same policy objective that we had before, with this extra KL constraint. That's all we're doing. All right? That's all this slide shows. And if you see, our objective is exactly our off policy objective that we put down in previous lecture. And we revisited in the beginning. Is this clear? Basically, is an expectation of states and actions sampled from theta old of the ratio p theta divided by p theta old of their advantages. Okay, so I want to change essentially the parameters so that I make actions that have high advantage, positive advantage more probable, and negative advantage is less probable. Okay, and I have this constraint, which is the KL constraint. What are we going to do next? Well, we'll consider, first of all, are we all clear of how to take the gradient of the main objective? Are we all very comfortable with the gradient of the main objective? Yes.
The delta here is the same as the epsilon condition, right?
Yes. I think we're all familiar with how to take the gradient. We said that you can just push the gradient in sign, and that's okay because the distribution with respect to theta old, and this is equivalent to, rewriting in this form. All right. Is exactly what we just discussed in the beginning of the lecture. So where we're going to focus now is on taking care of the KL constraint. All right, so let's see. What if we form the Lagrangian, and instead of having KL as a constraint, I put it as part of the objective, and I put a weight lambda in front of it, okay? So I get penalized when the constraint is violated. Okay, so I need to make sure that the delta becomes epsilon here, make sure that, sorry about this change in the notation. So what are we going to do? Well, we're going to form Taylor expansion. That's all we're going to do. And we're going to consider the first order Taylor expansion for our objective and the second order Taylor expansion for our constraint. Okay, and this is what you see here. In blue is the first order Taylor expansion for our objective, and in pink, the second order Taylor expansion for our KL objective. And this is what we're trying to solve. So let's see how we're going to do that. So we know what this is. We've said this 100 times. This is just the policy gradients. And here is the interesting thing. Does anybody know what is the KL of P theta old, P theta old? Yeah. And do you guys know how much is this? This square, grad theta, DKL, P theta old, P theta evaluate, that theta equals theta old? How do you know? No. Wait a second. The gradient, we need to form the gradient. It is not that simple, but let's go and check. Let's go and check that first order term. Here it is. Taylor expansion of the KL. We already took care of the first term and we said it's 0. Let's take care of the second term. All right. Who would like to guide us through the math? Let me start here by saying we're going to take the gradient of the DKL. The KL formula is right here that we can use it. All right. P theta always with P theta. Okay. And so how will this be expanded? Well, here we take log of the numerator minus log of the denominator, whatever you see there so far. Are you cool with this? So what will going to be our next step?
Second term should be 0.
Excellent. Yeah, so the second term is constant, so the second term is 0. This is great. Okay, so let's continue then with the first term. So what is the first term? Let's see. Let's use the chain rule for the logarithm. How would that look like? Okay. And the derivative of the inside the logarithm. Okay, sounds good. All right. So now let's, just to be more clear, let's write down the expectation as this integral. Okay, here it is. And the minus disappeared, but anyhow, I need to put it back. Is this really disappeared? Yes, it disappeared. No, it did. Minus. Yes, it disappeared. So sorry about that. There should be a minus sign in front. Okay, but let's assume it's there. And then what happens? Yes?
When we cross out P theta over, the gradient moves out and the sum of all probabilities is 1 constant.
Yeah.
The gradient of constant is P theta.
Yes. The derivative of constant is 0. Okay, perfect. That's why it's 0. So be very careful, guys. Don't say, oh, the KL is 0, and then I put theta all there and so on. No, we need to compute the gradient vector and then substitute with the theta old, okay? And it turns out that is 0 no matter what the theta old is here, okay? Yeah. All right. So we took care of the second term as well. So things are looking good. Let's look now at the second order term of the Taylor expansion of the KL. Okay, so here it's how it is. All right. All right, great. So, all right, here's what happened. Here, I've already did what your colleague said earlier, that the other term is just constant and actually disappears, okay? So the term that is parameterized with theta old and doesn't have any theta inside, it's already gone. Are you okay with this? Wait a second. All right. Okay, so let's just focus on this term. So we have the second order derivative. Let's just do one by one. So let's do the chain rule as before for the logarithm. Okay. So this is how it's going to look like. Do you guys agree? Okay. And who would like now to do the chain rule for the fraction? Okay, derivative of the top. multiply with the bottom minus the top derivative of the bottom divided by bottom square. Okay, this is how it's going to look like. Okay.
I got a question.
Yeah.
So for the second line, where is the cancel or this?
Which second line?
Yeah, the line below the box, long box. And in the middle.
Well, the square we just did. We said, okay, derivative of square is derivative of the derivative, and we took the first derivative, and then we take the second derivative. Okay, is this what you're asking? Yeah, that is exactly what we're doing. Okay, one at a time. Very nice. Great. So now what are we going to do? What do you think we should do? Well, I see this p theta square on the bottom that cancels with some terms on the top. Okay. And because it cancels, well, here's the thing. This little p theta x cancels with the p theta square. And this p theta, if you use the chain rule for the logarithm, you actually end up with something like that. Okay? Do you agree so far? And this one is actually exactly what we saw before. And again, it's going to be, constant. And then the derivative of constant is going to be 0. So the only thing we need to worry is about that second term. Okay? So let's see this second term. That's all we need to focus on. Sounds good. Okay, so it turns out that this formula is precisely the Fisher information matrix. That's how it's called, okay? The expectation of grad theta log p theta square. And here we have expectation, but we know we want to approximate, we can approximate those expectations simply by sampling trajectories. And this is p theta of the trajectory, and we know p theta of the trajectory is essentially p theta of the action from our trajectories, sample from theta old parameters, yes, of our policy.
We said the gradient, p theta, gradient p theta transpose contribution. Why didn't you the square make nothing?
1 second. Here?
Yeah.
Okay, yes. Where? In which of the two terms? Yeah, the second one. Who would like to answer your colleague's question? Your colleague is asking, where is this p theta x square on the second term? Exactly. So grad theta of the log will be 1 over p theta grad p theta. Okay? Great. Okay. So let's move on. All right. So we can approximate that this matrix. This is great. How big that matrix is going to be? Yes? Which is exactly the same as dimensions of theta, right? Is the number of parameters in our policy. Okay, all right, and n by n, exactly. Okay, so let's go back to our objective. Now it looks much more, let's say, succinct. And we have the two blue terms that comes from our policy objective and the peak term that comes from the KL. Okay. And we can go back and substitute for the information matrix because we just computed what is essentially this grad square DKL, and it's exactly this F theta old, right? And now we can go and actually try to solve that problem. How? By just setting the gradient to 0. So let's set the gradient to 0 with respect to D, okay? And essentially, the linear term essentially D disappears from there. And then the second order term, one of them goes away, and I rearrange the terms. And now my D step is exactly that. So look how beautiful it turns out to be. Instead of just using the gradient vector grad theta u theta, I pre-multiply that gradient vector with a square matrix, which is exactly the inverse of the Fisher information matrix, which I can compute from my trajectories. Okay? And that is called the natural policy gradient. Okay? And by the way, the notion of a natural policy gradient is not unique to reinforcement learning. At least a few years back, people were looking on natural policy gradients also for training deep networks. Okay, not reinforcement, just standard supervised learning, hoping that the optimization will be faster. Eventually, at least as far as I know, still gradient descent, like first order, no second order terms, still do better and people use them in practice. But for example, I want to say that for reinforcement learning, this helps dramatically. And the researchers that actually did that natural gradient research for supervised learning were the ones that wrote a very nice paper that ended up being a state of the art for reinforcement learning, because they proposed a very nice approximation of that horrible inverse of the Fisher information matrix, which is really, really, really expensive, right? There is no way we're going to do the inverse of that huge matrix, but they actually propose fantastic approximations. And, we can, I can paste the paper there in case you want to take a look. All right. Yes.
Sorry, what's the first contribution 0 when we extended the second gradient?
Yes, let's see. So why is the first contribution 0? I think you're asking here, correct?
Yeah.
In which, because in the first line also, I already threw away some terms. Are you talking about the very first line or?
At the end when we get to the equation.
Oh, yes, this guy here. Yeah, let's see. So if we have the expectation, essentially we have an integral per theta all, divide per theta all, the per theta alls go away. So we have essentially an integral of the grad square. The grad square will go outside of the integral. Okay, so you have an integral of per theta. The integral of per theta is? Yes. So you have a derivative of that constant, which is 0. Great. Yes?
So it seems like, what happened to the second term? I mean, we got two grad log p theta when we had grad p theta transpose over p theta squared.
Yes.
I'm just curious, where did the logs come from?
Well, yeah.
We have p theta expressed in the denominator.
Yeah.
So if you take derivative of log, it's 1 by x.
Yeah.
2 logs, 1 by x, 1 by x from both.
Oh,
I think
I
that's.
see. So we're
Yes.
kind of backtracking.
So grad theta log per theta is exactly equivalent to 1 over per theta grad per theta by the chain rule for the logarithm. Okay. Okay. Well, great. By the way, do not worry, because state-of-the-art model free RL, which is motivated by the discussion we're saying here, how I want to update my parameters without changing my policy that much, will not go through this type of second order information and estimation, will be very practical, and it works very well in practice. And we're going to see it on the last slide of today's lecture, okay? But it's important to know this, and there was a very nice NeurIPS paper, natural policy gradients, proposing exactly this way of, taking gradient steps and so on and so forth, which I think is one of your readings today. Okay. All right, so now we know the direction, but the natural policy gradient. Now we know the direction, but next to the direction, we have a scalar that we also need to compute. What's your question?
When we take the derivative of the second term with respect to t, would it be like 2 times t or just 1 times t? When we have the d transpose.
I see. So you're saying maybe the 2's need to cancel there.
Yeah.
Yeah, I see. Okay, yes, I think that might be a typo. Okay, great. Thanks for pointing this out. I think it is on all the, it stays there on the lines. Okay, great. Thanks for pointing this out. Other than that, are you cool with the derivation? Yes.
I'm actually curious, is there any intuition for why second order methods are worthwhile for RL and not for supervised learning?
Yeah, exactly, for the things that we're discussing, that the step size in reinforcement learning matters way more than the step size in supervised learning, because of this iteration between a policy and data collection. So if your policy becomes worse, if you go too far from your initial theta, your policy is worse, the data this policy is going to collect are going to be worse, and then things are going to go bad. Do you see? And also, why the problem is not to take too small step. For example, in supervised learning, you can have very small learning rates, right? here there is a problem, because if you take very little step, then again you need to collect experience. So you are paying on experience collection. Does this make sense?
Sure.
While in supervised learning, okay, sure, I have lower learning rates. Sure, some people have showed that the schedule is important, and if your learning rate is more aggressive in the beginning, essentially you find a better optimum and so on. But variance of the learning rate will not dramatically change your final result. All right. Basically, what we said in the beginning of in the first slides, that's why step size is very important for RL, because of this, the fact that the data changes and policy changes and you collect data under the new policy and so on. Okay, so we are ready now to take our theta nu based on theta L plus alpha multiplied instead of G, which was the policy gradient, by Gn, which is the natural policy gradient. Still there is a scalar though, instead of that Gn, and we need to compute that scalar. And how we'll compute that scalar? Well, we'll say, I want my KL to be at most epsilon. Okay, that's all we're going to say. And based on that constraint, and so it is very easy to set up that, upper limit, let's say, of the KL, and you'll see how this is going to show up again later in the lecture. Then you can compute essentially this scalar in the following way. Okay, I will take the KL approximation, the second order one. I know my first two terms cancel, and the only term that survives is the second term. I set that second term equals to epsilon, and here is, I solve with respect to this step alpha, and this is the scalar, okay, that I get. This is just the scalar value. So now we're ready to put everything together. My theta nu equals theta L plus alpha Gn. I know exactly what is this alpha. I know exactly what is this Gn, okay? And this is precisely the pseudocode behind the natural policy gradient. Which is an earlier paper that showed how this is important for making sure that this policy iteration is essentially stable. Does this make sense? Okay, so let's look at how it looks like. We start with some initial parameters of our policy, okay, and we iterate. We collect trajectories. We estimate the advantages, AP, because advantages depend on the particular policy you have. During our favorite advantage estimation algorithm, if you remember, the advantage estimation we used was you use MC or TD to estimate V, and then use the value function to compute the advantages with some n-step, TD method. All right. Then you form your policy gradient, and you form your KL divergence Hessian, which is also called the Fisher information matrix, and its inverse F minus 1, and you compute the natural policy gradient update. And this works really well if the parameters of your policy are few, very few, okay? And indeed, reinforcement learning existed before 2013, and indeed the policy networks were very small because they were operating over engineered features, all right? So you had few parameters, so this was not actually difficult to compute. Now, the problem is that once you use policies with many, many parameters, computing this Fisher, the inverse of the Fisher matrix, is actually extremely difficult, okay? So what are you going to do? Well, you're going to approximate it. And this is exactly the contribution of this TRPO paper, Trust Region Policy Optimization. Yes?
I was curious, did this come from inspiration from something like the Newton's method or any other existing second order methods?
Yes. Well, I would say this is the most natural and intuitive thing to do. If you say, I want to make sure when I take steps, the KL of my policy doesn't change more than a specific threshold, right? I mean, the way we motivate was extremely natural. We said, instead of putting bounds on the norm of the parameter states, we want to bound the KL of our policies for different states, right? That was super intuitive. Right? Other questions? Yes?
Is this pseudocode from the TRPO?
No. This is from the natural policy gradient paper.
Oh.
Okay? Which is much earlier paper, and it is from the era where policies had very few parameters.
Did ever this code, like, implementation of this found accessibly online? Because I'm just curious, it seems very simple to implement.
Yes, so it doesn't seem very simple to implement. Does anybody want to comment here? What do you think is the most complicated thing here?
The Fisher.
But this Fisher, but we showed how to compute. But beyond the Fisher thing, is the rest cool? Do you feel cool with the rest? For example, for the jihad, do we all know how to compute it? Right? We spent 2 lectures on that jihad. It's not that hard. We'll take this expectation, overall states and actions over trajectories, right? Grad p theta of alpha divided by p theta alt of alpha multiplied with advantages. Advantages we know how to compute. We'll compute the value function, right? And then the advantage of an action is what? Instantaneous reward plus gamma to the correct power v of the next state minus v of the present state, okay? So we have the advantages. I can compute the jihad. Everything is great there. So we are happy with this. What else we need to do? Nothing. The only thing is this f hat, correct? And how do we compute f hat? Let's see. And then when you take the inverse, I understand. Let's see here. We had it. That's it. This is how we'll compute it. You'll take trajectories, essentially state actions, and you'll be computing grad theta log p theta of a particular action, and form essentially the square matrices and sum them up.
Are we not going to run into like this underflow, overflow, instability? Is it inverting a really large matrix and then multiplying with vectors and then?
Yes, let me tell you. So that paper did not have a very large matrix. Okay, it had a parametric policy with a few dozens of parameters. Okay, so it was very easy. It was very easy. But let's see, TRPO, by the way, you don't need to implement any of those methods in your homework, I think. I don't think you have to implement them, okay? But let's see. But quiz 2, we definitely ask. We ask, what does TRPO do different than, let's say, natural policy gradients? What does PPO do different than TRPO and so on? Okay, so we just ask the difference between the methods. So let's see. So TRPO, it's a more recent paper. By recent meaning is after the, let's say, 2012. This is what we mean. And is from the era where policies were neural networks, and indeed they had many, many parameters. And essentially, they form an approximation of that inverse matrix. They never actually use it. They never actually compute it. They form an approximation of this xk, and they fit it there with conjugate gradient. All right? So you can see the approximation of that. You can use any standard approximation, that people use. And this is also what this paper proposed. So that's one contribution of that paper. The second contribution that shows a let's say, theoretical result, that if indeed you follow this natural policy gradient, you have some monotonic improvement of your policy, that indeed, you have some guarantees that the policy is going to converge and is going to diverge and so on, which there didn't exist till that paper showed up, okay? Another thing is the following. Instead of computing the scalar in front of the natural policy gradient that we just discussed, these people do just a line search. So what does mean a line search? They search on different places of how much they can change their parameter vector along the natural direction, and they see the KLs in different states. And if the KL changes too much, they backtrack. They say, okay, let me not move that much. All right. So they just search for the best scalar across this natural direction. So that's all. Yeah. So essentially, they have the direction, and then they try for different, alphas, scalar alphas along the direction, and they want to make sure that both their objective does well, which is the policy objective, and the KL of the policy in different states is bounded. And if this is the case, then they accept the change, else they backtrack. So they do exactly what is super, super intuitive to do. They just make sure I want to move as much as I can along my natural gradient direction without violating the KL constraint, for all the policies, for all the states of my policy, and making sure that my objective goes up. Okay? So that's all.
What was the first contribution? I think you mentioned a theoretical one, blind search, and then the first thing that you mentioned about the other, I missed that.
Well, they proposed the practical implementation for a natural policy gradient method with this approximation of the inverse of the Fisher matrix. Okay? Yeah.
What is CG in the
Conjugate gradient. Okay? So they form, actually we had TRPO as part of the homework, but actually we removed it because people mostly now use whatever we'll discuss right now. Okay, guys? So so let's just jump to see some simplifications of these natural gradients. So proximal policy optimization. So can I achieve similar performance without ever using second order information, without computing or worrying about the Fisher information matrix? And PPO paper gave two different solutions or answers to this question, okay? And one of those answers is actually what most people use, and it's called the clipped objective, okay? So the first is as follows. We have again the same unconstrained objective, which combines our policy gradients with the KL. So I want to make sure I maximize the objective of my policy, the advantages essentially of the sample states and actions, while not, increasing too much the KL divergence between the theta nu and the theta old, between the probability distribution of our actions that the theta nu and theta old assign. And so they say, so we have different coefficients in front of that KL penalty, and those coefficients change between iterations to make sure that they enforce this KL divergence constraint. Now, the second solution is very, very interesting, and it looks like this. They say, we're going to form a clipped objective. So again, I have a big summation over all the actions, over all time steps for my trajectories. And for each one of them, I optimize this mean, RT theta of its advantage, and the clip of RT theta 1 minus epsilon 1 plus epsilon of multiplied with the advantage. And we'll see exactly what this clipping allows you to do. Okay? Yeah. So let's see. Let's take a closer look on that clipped objective. All right. So this is the first solution. They say take several, gradient descent steps over optimizing the scale penalized objective, and at each time step compute the KL for different states between the P theta old and P theta nu. And if you see that this D essentially is large, make sure you increase the penalty. And if it's small, make sure you decrease the penalty. That's all it says. Okay. And the clipped objective is exactly that. Let me just remind you, first of all, our initial objective, which is an expectation over states and actions, the ratio of the probabilities of the actions under the new and the old policy multiplied with the advantage of a particular action. Okay? So these people say the following. We are going to form, instead of optimizing directly that, I want to make sure this RT theta, that ratio, does not change too much. What will be the initial value of that RT theta? When I start thinking by gradient steps, 1. Because I've collected some bunch of trajectories with my current parameters, correct? And now I start taking gradient descent, so the theta start deviating from that. In the beginning, let's say that this RT theta is 1. So I have exactly the same probability under my old and new policy. So I want to make sure that for my sample states and actions, this ratio does not become larger than 1 plus epsilon or lower than 1 minus epsilon. Do you see what I mean? I want to make sure that my new policy does not change the probability of actions more than epsilon. Is that clear? Yes.
In addition to the KN constraint, or
No, you throw away the KN constraint. Okay, that's the only objective you need to optimize. Do you see the intuition, the high level intuition? Okay, so let's see why this clip objective take this form. Let's see. First of all, what does clipping mean? When you clip a quantity between alpha and beta, means that between alpha and beta, that quantity stays unchanged. Above beta, if the quantity goes above beta, then is equal to beta, and if it goes below alpha, then is equal to alpha. This is what the clip function does. Okay. So here, that clipping essentially clips this RT theta, this fraction, to be between 1 minus epsilon and 1 plus epsilon. It doesn't allow it to change more than that. Is that clear? So let's see how this is relevant. Let's look at the different cases where the advantage of a particular action is positive and the advantage of the particular action is negative. So let's consider an action which has a positive advantage. Okay, so we'll start, the RT theta will start, this is the R, this is the ratio. We'll start, let's say, from 1. Okay, and what will the network try to do? We'll try to make that action more probable. Okay, so this means that during gradient descent, this is going to push higher and higher and higher. We'll make that p theta alpha higher than the p theta all of alpha. And then at some point, the ratio is going to hit 1 plus epsilon, and then it's going to be clipped. So what does clipping mean? It means there's no more gradient passing through there. Okay, then you stop the gradient. Is that clear? So then you don't allow the policy to keep improving and increasing the probability of that action, because you know that your advantages are not going to be valid anymore because your policy changed too much. Okay, with this? Okay, now who would like to tell us what's going to happen if the advantage of a particular action is negative? Let's say, by the way, just don't be confused. Let's forget about the minimum. I'm going to talk about the minimum in a second. Let's just look at the clipped objective for now, the second part of this minimum, okay? And try to understand that part. So we saw what happens when the advantage of an action is positive, all right? Essentially, this clipping does not allow, the network does not allow gradient descent to make this action much more probable than how it was in the previous policy. What will happen if the advantage is negative? Yes?
We'll just make it so it can't be much more less probable. It can't be much less probable. So we just go like a
right. Correct. Yes. And by the way, just to be clear, once you clip, there's no more gradient passing because it's a constant after that. All right. So gradients pass while this ratio is between 1 minus epsilon and epsilon. Okay. So we're cool with this. Now, who would like to tell us what this minimum is actually doing? Why there is not just this clipping objective? Why we need to take the minimum between RT theta multiplied with the advantage and that clipping that we just discussed? Yes.
The minimum would let you select the worst thing possible and optimize based on that.
That's true. Yes, it's gonna. Right. That's right. Between the two, correct? And why this is important?
So it's going to minimize, so it's going to set a minimum of the update that you can do at the clip objective, and the first one is to make sure that in case that the change that you're trying to make, that if the advantage is negative enough, that you still do want to make the change, it will let you make the change.
Mm-hmm. Could you repeat your reasoning? So we can discuss about if when the advantage is, let's say, positive, okay? And essentially the minimum between RT theta alpha and this clipping would be what in that case?
In that case, so if the advantage is positive, then it will try to make sure that you don't change more than RT theta plus minus epsilon? And if it is negative, I guess it will try to push it as far as it can near the epsilon boundary around 1.
Okay. Yeah. So, all right. So here's the thing. Once you take gradient steps with respect to your mini batch, you don't only change the probabilities of actions in your mini batch, you change also the probability of actions outside your mini batch. Okay. So here is a new action shows up, and this action has positive advantage. All right. And somehow you've already, clipped it. Essentially, you made it already, essentially became already very improbable because you made sure that you put very low probability on that action. So by taking the minimum, then you would be able to jump to the left term and still, take gradients and essentially recover. Yes.
Is this like if advantage is positive, then like you would, if advantage is positive and your like ratio is smaller than 1 minus epsilon, then like you're doing it less.
Exactly. So if you don't want a good action with positive advantage to have a ratio less than 1 minus epsilon. Exactly, which can happen because other actions may have updated the parameters of the integral so that this is the case. So now by taking the minimum, that first term is activated and gradients start flowing to push essentially this RT back up. Okay, great. Exactly what your colleague said. Do you see?
Same thing if it's negative, right? If advantage is negative.
Yes.
If RT becomes positive. So if it's doing it more, then you might not also want that. And then the minimum of those two terms might also be the left term. If advantage is like very negative and RT like is going greater than 1 plus epsilon, then the minimum will also be the left hand term. In that case.
Exactly. So if the advantage now is negative, okay, then and the clipping is 1 plus epsilon and above, then again the left term will activate and will kick in gradients and try to correct it. Okay, exactly. This is precisely the intuition. The reason is that we operate over mini batches. Parameters that you take under these actions can change other actions in arbitrary ways. And you want to make sure always that, positive advantage actions are not much improbable under your current policy and negative advantage actions are not very probable under your current policy. This is what this says. Now, why I'm presenting this to you guys, I think this is an extremely simple method. It still is used all the time in papers. It is one of the, a baseline that you typically use. In fact, we're submitting a paper tomorrow. This is one of the baselines. And now you know it, and it's super simple, and it's extremely easy to code up, and doesn't use any second order term, is very fast, and so on and so forth, right? Yes, please.
I'm sorry, so if RT of theta is negative, then there's minimum values RT.
Well, 1 second. Who wants to ask this question? So wants to answer. He says, what if the RT theta is negative? That's what your colleague said. So who wants to say something here? It cannot be negative. Why RT theta cannot be negative? Yeah, RT theta is a ratio of probabilities, exactly. So it cannot be negative, okay? Yeah. Other questions? Okay. Okay, so this is how the pseudocode looks like. Same as before. We have some initial parameters. We have iterations. Under my current policy, I collect a bunch of trajectories. I estimate these advantages the way we have described, going through our critic, computing the value network, and then estimating the advantages. We compute the policy gradients, and we take steps of the mini-batch, stochastic gradient descent steps under this clipped objective, and the clipping automatically is going to switch on and off the gradients for different essentially examples. That's all. Okay. Yeah, and it's simpler to implement and works as well as the other suggestion of that policy. And you can read that paper, at least pick the parts of the paper that are, clear, and they actually show the intuitions that we just discussed. And you will see comparison to other methodologies we see. So, for example, this is A2C. This is what we just covered in our previous lecture, if you remember, right? Policy gradients without having this taking care of how fast the policy changes and so on. Cross-entropy method is something that we'll see in later lectures. TRPO we just discussed. And as you see, PPO is actually doing very, very well while being much cheaper, than TRPO and not much more expensive than A2C, which is the vanilla policy gradient actor critic method we saw without worrying about the step size. Okay, so today's lecture we just said that if you worry about the step size, how much you change the policy objective under the same policy objective that we had in the previous lecture, actually you will be able to do better. Okay, yes.
Sorry, what's the y-axis here?
Yes, so the y-axis is rewards that you get from the environment. Your goal is to maximize the rewards, and very good question. So the y-axis is average rewards, and the x-axis is the experience you collect. So we want the curve to go up as soon as possible, right? You want to maximize your reward with as little experience as possible. So this is the end of today's lecture. We have office hours. Yes, please.
Also, so for example, in PPO, we see a lot of variance happening, a lot of jitter happening. So if we reduce the value of epsilon, would it be smoother?
No, good. Let me tell you, a lot of this jingling that you see has to do with how many trajectories you collect. The more trajectories you collect, the more reliable your advantage is, the better your optimization. The more clusters and the more effort you put on parallelizing your collection of experience, the better your vanilla RL algorithm is going to do. The same algorithm under, insane blow up resources will do way better than, same method, same pseudocode with little resources. So I think this is the key to making your, performance kind of more smooth. All right. Now, having said that, there is a lot of intense discussion in the reinforcement learning community about the importance of running the same experiments under different seeds, okay, random seeds, and evaluating performance and taking averages and showing not only the mean, but also the deviations, so that you can see that, look, this method is much more, let's say, consistent across different random seeds versus, this method actually has huge variance across different random seeds and so on. So this is also extremely important to the extent that they have now a questionnaire each time you submit a paper to NeurIPS. Did you run your experiments with multiple random seeds? Okay, so you need to answer these questions whenever you submit a paper. So this is insanely important. Okay, but yes. But basically, you can still find excellent papers that the only thing they say is, look, we took PPO and go at the collection of experience and across multiple agents, and look, we do actually really well, and so on and so forth. And in fact, we may be able to visit some of those papers later in the course when we're going to start talking about real applications, etc. Other questions? Yes.
What is like the standard number that are used?
How many random seeds to try?
Yes.
I mean, depends on your resources. The minimum is 5. People say I used 5 or 3 for random seeds.
Really bad reviews with 5 though.
With 5, yes. So you want.
Reviews are like, this is not enough.
Right. So you want to do as many as you show that your variance is actually, you keep running your method, then you see that you're within the bounds that you decided. Okay. Okay, great. Please come for then more personalized question answering right outside the amphitheater.